So now what we are going to do in today's class will also really help you with that homework in terms of understanding the details, because we are just going to be reviewing whatever we did, but also a lot of things which were kind of implicit in what I did in the big picture. We will get into some of the subtleties of that in understanding the things a little more explicitly as to how it gets into problems and things like that. So I really want you to pay as much attention as possible to this particular class, because it's kind of bringing the whole 10 weeks into one, let's say, set of lectures, because this will include the next 2 or 3 lectures as well. But this essentially gets you into the actual variables that are involved, which were kind of implicit in whatever I showed earlier, and that will become much more clearer. We will start with a few simple examples, and then we will try to generalize that. So this, for example, could be the front view of your wing, aircraft wing, and subjected to a certain lift distribution, and because of which it is undergoing a certain bending. So this is where the fuselage comes in. So the attachment to the fuselage of the wings for most of the flight is such that the deflection is kind of symmetric on either side, unless certain specific maneuvers and or rotations are being performed, in particular associated with rolling or yawing. Otherwise, you typically have symmetric, in which case it means that there are 2 ways that you can model this whole wing. One is you can think of this as a simply supported beam, which very few people realize, that you can think of the 2 ends of the tips of the wings as to be hinged, and one of them is on rollers. So then you can see what really happens. Another more simpler way, and which is more commonly used, and which is also the right way to do it, is to consider just half the wing because of the symmetry involved, and then treat this as a fixed end and this as a free end, and then there is a load distribution on that which is making it bend like this, right? So we will focus to start with on just a 2D description of the motion. In other words, we are not bothered about what happens in the z direction, which is coming out of the plane of this board, because remember that there is drag and also thrust, because of which there is a bending that happens in the other direction as well. But if we understand this bending, the bending out of the screen or into the screen is very similar to understand, so you will not have anything new to add to it. But we will go to that as well. Once we are done with this 2D deformation, we will get into the 3D kind of deformation and show you what happens for bending in the other direction. Okay, so our focus is on trying to get to this deformation. First of all, we need to have some motivation as to why we need that deformation. What is the utility? Suppose I am able to solve for v of x as some function, let's say some quadratic function or some cubic function, whatever it is, depending upon how the load distribution is. Once I get to v of x, what can I use it for? How does it help me? Why even bother about getting to that? Any leads on that? Is it at all important? What if it is, of what use is it? Okay, let's see. There are many utilities for this, but we will look at 3 important ones. So the first thing is recollect that we went into 3 kinds of designs. One is all of them starting with an S, a strength-based design, a stiffness-based design, and a stability-based design, right? The last 2 had everything to do with this deformation, right? So essentially you are trying to minimize that deformation because the aerodynamicist has given you a certain optimal shape for the aerodynamics to perform at its best, and you want that shape to be retained as much as feasible. So once these deformations are going to take place, all that displacement is going to modify your overall shape and how the wing phases the air, and therefore what the forces are. So it's going to have repercussions for that. So how large the deformation is. Whereas from a structural design point of view, it's the strength that is most important, and which is why we considered that first amongst the 3 S's in the initial classes, because that helps you make design decisions in terms of which material to use to make your wings, etc., because you want all of your stresses, even in the most difficult of maneuvers and whatever high G loads that are going to come in the VN diagram, you want those stresses to be less than the failure stresses of the material. So it helps you choose the material. And it's not just less than, but less than by a certain factor. And there are specific ways in that, in the way in which that factor is defined, usually about 1.5 for most aerospace designs. But essentially what you're trying to look at is not only is that important, though that is one of the most important things, but when you're designing the structure, the deformation also becomes important, because you also have certain maximum limits in that deflection that you have. If this tip deflection is of the order of a few meters for typical large passenger aircraft, so which means that if it goes beyond a certain limit, it can completely alter your overall airplane response itself from an aerodynamics perspective. So which means that it has to have certain maximum deformation limits also. It has certain stress limits that is taken care of typically by the material, but you also have certain geometric design features that you have to build in, so that the deflections or rotations are not larger than a particular value. Okay? So sometimes the active design constraint is therefore based on the stiffness or the flexibility, which is what we said, strength based design, and then we looked at stiffness based design. Okay? So that's one reason. The other reason, which I did not touch upon in the earlier class, but it was implicit, was that there are 2 classes of problems, ones which are statically determinate and the others which are statically indeterminate, right? So now the example that we saw of the wing was a case where I said you can either treat it as simply supported or a cantilever. Cantilever would mean the one end is fixed, the other end is free. The other case would mean that simply supported would mean that one end is on rollers and hinged, the other one is hinged without being on rollers, right? But here we have a complex combination of both. One end is fixed, the other end is hinged. Okay? So when you have something like that, this becomes an example of what we call as statically indeterminate structures. Okay? And it can apply to plates and other kinds of structures as well, but our focus today is on beams. So we are talking of statically indeterminate beams. So indeterminate obviously means you are unable to solve. And but we are qualifying that by saying statically, which means that if you use just the static equilibrium equations, then you will not be able to solve for this problem. Okay? So, but you will still be able to do it if something else is done, and that's where the question gets answered, that why beam deformation, because without going to beam deformation, such a class of problems which are kind of little more constrained than required, then you really need to get to deformations, even to get to stresses and the other things that you're interested in. So therefore, from that point of view also, this is very important. When you're applying certain loads on this structure, taking this as an example, if you there's a vertical load or there's a moment applied on this, etc., it's going to resist that. Like any structure, when you're applying something, Newton's third law gets into action, and so every action is going to have an equal and opposite reaction, and that equal and opposite reactions are what we qualify as bending moments and shear forces. So bending moments and shear forces, remember, are not applied loads, but are the reactions of the structure at each cross section to any applied load that you have. So you could have a distributed load, like an elliptical distribution, like what you have in aerodynamics for a wing, fixed wing, and you could have concentrated loads, like coming from the weight of the engine attached to it, the thrust of the engine, etc., or any other things that the weight distribution, which could be another very different as a function of x compared to the lift and or drag. So all those loads put together have to be resisted by the structure, and that resistance can be modeled, of course, is in the form of stress at each point, But if you look at a cross section as a whole, then we can see the overall effect of that in terms of what we call as shear forces and bending moments. And you'll see this a lot in today's presentation. All of this was kind of contained within what we already did, but now we are bringing it out a little more explicitly, right? So as I said, statically indeterminate means we can't find just by using the static equilibrium equations. What we would have done if this was not there is that we would have put the overall beam into a free body diagram and removed this support, and what all reactions can come from this support, we will put that and we will try to solve for it by your usual statics equations, summation F equal to 0, summation moments is equal to 0, and then you will get to them, and then you will be able to find things. But here it becomes a little more challenging because you have more variables than you can solve for by just using those static equilibrium equations. So which is why there is a prerequisite, and this prerequisite is that you need to find the deformations first, then only you can get to even the stress to get to the strength based criteria, right? So now here is an example that I've given where one end is fixed and the other end is on hinges, but you could also have a fixed case, both ends are fixed. That's also even more of a statically indeterminate. In other words, the level of indeterminacy is even more for a fixed beam than compared to the fixed hinged or fixed hinged on rollers kind of a beam. Okay. Now there are, because this is a two-dimensional problem, as I said, in other words, the beam is a one-dimensional body, but we are looking at its deformation just within the plane of the screen, and which is a two-dimensional plane. Okay, so where we are introducing x-axis along the length of the beam and y-axis the direction of the deformations. But in general, it can also have an elongation. Okay, so which means that there is a u and there is a v. A u is along the length of the beam and v is perpendicular to the beam, and v is what is related to the bending displacements, whereas u is essentially for an axial force. We will not focus as much on this today. We already discussed this in quite threadbare manner in the end of last class. So, but just for completeness sake, for a 2D problem I have listed, there have to be two displacements for a 2D problem, but also one rotation, and that rotation can either be specified, or if the rotation is unknown, the moment at that location has to be specified. So in other words, these are contemporaries of each other. They are in some sense conjugate of each other. So either you specify a rotation or you specify a moment. You can't specify both at the same location. Okay. So at some locations only moment is specified, like in the right end, and some locations only the rotation is specified. Same thing holds as far as the displacement and force are concerned. They are again conjugate to each other. If you specify the displacements, you cannot specify the forces. The forces become unknown. The reaction of the support is the forces corresponding to u and v, F1 and F2, let's say, and those are unknown to be determined. On the other hand, if you had, let's say, a free end over here, you would be specifying the forces and you wouldn't know how much it is going to be extending and all that. So you will have to specify that. Okay. So I'm sorry, this has, if it's on rollers, u cannot be 0. It has to be without the rollers, it's just fixed over here. The hinge is fixed. So which means that you cannot specify this and you will have to find the force. But whatever it is, the overall idea is that when you have fixed free, then you can have statically determinate structure. But once the other end is either hinged or hinged on rollers or it is fixed, then it gets into a statically indeterminate form, right? And many geometries, geometric boundary conditions compared to the natural boundary conditions is the reason why this is a statically indeterminate problem. So in other words, for example, over here, you have the number of geometric boundary conditions. So assume that this is not on rollers, it's fixed over here. So then what you would have is that u equal to 0, v equal to 0 are all displacement boundary conditions. This is also a displacement boundary condition. This is a rotation boundary condition, a generalization of displacement. So in other words, you have 1, 2, 3, 4, 5 conditions which are geometry based, and only one which is force or moment based, which is natural. So in other words, there are many more what are known as geometric boundary conditions or Dirichlet boundary conditions, whereas very few natural boundary conditions, or what are known as Neumann boundary conditions. Okay? So in other words, the number of boundary conditions in terms of u's and theta's, v, etc. is much more than compared to this, and which is why you need to get those displacements first before you can solve for the reaction forces and or the stresses involved. So that's essentially an example. We will revisit this. Right now we are only taking up motivations for why we are looking at beam deformation. So we have looked at one, that you don't want deflections to be really large. You want to limit them by a certain amount. So you want to set like maximum stress limits. You want to set maximum deformation limits as well. The second one is to be able to treat these kinds of statically indeterminate problems. Though the wing is not an example of that, there are many examples within the aircraft of structural components which are of this kind, like some of these spars and or the stringers, etc. Depending upon how they are attached to the rest of the structures that they interface with, many of them could be statically indeterminate structures, and that's why this is important even for aerospace engineers. The last reason that I would like to give amongst the major reasons for why we need to understand beam deformation is that this is going to help us in the dynamics, and this is in fact the feature that we brought in when we talked about the stiffness based criteria. We went into a square root of E by rho because we were looking at dynamics, trying to see how the natural frequencies can be handled compared to the loading frequencies, which means that this deformation is going to be important from a structural dynamic perspective. And in structural dynamics, we are interested essentially in three quantities: the responses, the natural frequencies, and the mode shapes. And all of these will be affected by the deformation. So it's important to determine the displacement field and how it varies both with space and time in order to be able to get to all of these quantities. Okay? In addition, we go beyond structural dynamics to aeroelasticity. Once again, the couplings that will be involved with aeroelasticity will make this need for deformation very, very clear. Finally, in terms of the overall response of the vehicle itself, here we are talking about the response of an individual structure, let's say a wing or a spar or a stringer, etc. But here we are talking of the whole vehicle, the flight vehicle structure, an aircraft or a helicopter or a rocket, etc. Its response also depends on how these individual structures are deflecting, how much they are rotating at each cross section, etc. Those kinds of things become critical over there. In other words, we will be able to determine whether the aircraft is operating in optimally or suboptimally. Is it stable or unstable? Okay. The instability could again be in the form of dynamic instabilities or static instabilities. Examples of dynamic aeroelastic instabilities are flutter. Example of a static aeroelastic instability is what we call as airfoil divergence or wing divergence. So that's all of those can be analyzed, and whether they occur or not, and if they occur, how to postpone it. All of these decisions can be made if and only if you had already found expressions for your beam deformation. So these are three sets of motivation that I have given you for the need to get to V of x. Now that you are satisfied that we need to get V of x, we will get into the procedure of how to get to V of x. Okay. For that, we first need to introduce an axis system, certain variables associated with it. Not only we have the x-axis along the length of the beam and y-axis, the direction in which you are applying the loads, which is the lift load predominantly in the case of the wing, and where the deflection is taking place. Is all deflections in x direction we will call as u, but we are not concerned about that right now, because the classical beam has only transverse deflection. So that's V of x that we are talking about. And V is along y, but it's a function of x. You can see that here it is 0, and slowly it is becoming more and more. It's deflecting much more. So it's this distance from its original location to after the lift has non-zero lift has become a finite lift. Then you see that this is going to go up. It's going to bend up. These wings are going to bend up. So how much is getting deflected? Obviously, it's a function of x, and that's what we want to determine over here. And in order to be able to do that, just this view is not enough for us. We need to cut this at a particular location, arbitrary x location, what we call as a cross section, because we are crossing this and we are getting into a section of the beam. So therefore, it's called a cross section. This is a cross section. So it could be any arbitrary shape. In our case, of course, it's an airfoil cross section, but it could be whatever we are deriving can work for any arbitrary cross-sectional shapes, including what we have shown over here, right? So now, if you're looking at this, you see that, maybe I think I didn't put it in the, yeah, sorry. I should have put it in the presentation mode. Okay. Now coming to the cross section, we again need to have coordinates. One coordinate is already there because we have introduced y already, which is in the plane of the cross section, but we need a second coordinate, which is what is z, which is in this picture coming out of the board, but here you can see it explicitly over there, right? So when you see that, there are 3 quantities which are along the y direction and 3 quantities which are along the z direction for this very simple problem. The quantities which are along the y direction are the load that I apply, in this case the lift distribution, and the response of the wing to it, how is it reacting as per Newton's third law, that is what we call as the shear force. And then there is a deformation that takes place, which we already pointed out over here and which is what we are setting out to determine. So all those 3 are in the y direction. So it's very important to remember that. But there are 3 other important quantities which we will get to shortly, which are in the z direction that is coming out of the board. So it is x is having a unit vector I tangential to it, and y is having a unit vector j tangential to it. So if I cross j, I get k in the right hand thumb rule that has to come out of the board, which is what we are showing over here. And along that is what we have, because of the lift distribution, there is a bending moment. So that bending moment you can see is in the positive z direction, and that's what we are indicating as Bm over here. In addition, to be able to determine that Bm, we will, and the stresses associated with it, we will see that we will need what is known as a second moment of area. Okay, the second moment of area, many people call this inertia, but you should not get confused between the moment of inertia, which is having the units of mass times distance squared, whereas this is having the units of meter power 4, as we shall shortly see. But this is also about the z-axis. Okay, the moment is about the z-axis, the I is about the z-axis, and the curvature that results because of that, that curvature is also in the z-axis. So when there's a deflection, its first derivative gives you the slope, the second derivative gives you the curvature, and all of these are in the z direction, as we shall see shortly. And when we do that, it's important for us to keep both these cross-sectional dimensions in place. And the determination of this point O, where the origin within the cross-section, is also important, and there are no unique choices for it. Depending upon the analysis we are doing, certain points are more convenient than the other, but once you have made the choice, you have to stick to it consistently. So for most of the work that we will be presenting in today's class, we will be looking at O being the area centroid of this particular cross-section. And we will get to the definitions of what is an area centroid, though you will be familiar with it from previous maths courses as well, but we will just briefly review that. So now, first thing to remember is the beam reference axis, which is what we call as the x direction, and the cross-sectional coordinates y and z. For the beam's deformation, in just because of lift, as you see over here, not because of drag, which is coming out and or into the plane. So that is something that we can generalize as an extension. Right now, let's focus on deformations happening within just the xy plane. Okay. So for beam deformation in a 2D cross-section, that is the YZ cross-section, the applied load is along y. So you see that that is the direction of the load, the lift distribution. Okay. Then you have the reaction of the cross-section, which is in terms of a force as well as a moment. The first one is a shear force. So it's happening within the beam at each cross-section. and that is again along y, the same direction, okay, in which you are applying the force. The reaction is going to be equal and opposite. It's going to be, of course, along the other direction, but essentially parallel to the y axis is what we mean by that, right? Now coming to the bending moment. So again, within the beam cross section, it's also an internal reaction, but now that's happening about the z direction because this is bending this way. So essentially the bending moment is a vector acting in this particular direction, right? So because it's I cross j. Next is the deformation that's happening along the y direction, and which is why we give it v. If it was along x, we would call it u, and if it was along the z direction, we will call it w. So u, v, w corresponding to x, y, z, right? So right now our focus is only on the y direction deformations, which is v. We are not talking about u and w, okay? So deformation is along y. For now we also assume, but it's not shown in this picture, but we will assume that there is a symmetry about the z-axis. So in other words, how the cross-section looks below the z-axis, exactly similar it should look above the z-axis. That will bring in a lot of simplicity to some of the things that we are going to do, which we will take for now, but we will relax that assumption later on. In the case of the aircraft wing, where that is applicable, this assumption is, for example, when you're having a symmetric airfoil cross-section. So in other words, let's say NACA 0012, for example, or any of the 00 series in NACA series, you will see that it's essentially the NACA series, if you call it that way. So essentially you see that for all of those airfoils, there will be no camber, and therefore you will have symmetry about the z-axis, which is essentially the xz plane for the wing, okay? So now, as I said, this is an unnecessary and irrelevant assumption, like what many of the things that we pointed out in our generic thing. Here we are only reviewing that. So this is another example of that, just to keep things simple and tractable for a pedagogic purpose, just for teaching and learning. But later on, we will relax that in today's class itself, if not in the morning, in the afternoon. And then we will see how it can be extended when you do not have a symmetric cross-section. You do have a camber in the airfoil, which is more common. Okay. Now coming to the curvature. So as I said, there is a displacement. Because of the displacement, there is a slope, its first derivative, and then there is a curvature, which is its second derivative. So we want to get to that curvature because it's in a way indirectly measuring your deformation. Okay, so and from curvature we can integrate backwards twice to get to the deflection via the slope. Okay, the first integration of the curvature will give you the slope. The second integration, that is, if you integrate the slope, you will end up with the deflection, right? So that's why the curvature is a very, very important measure of beam deformation, and that's what we are going to focus on over here. So right now, as I said, we have only one displacement field, which is v of x, and that's parallel to the y-axis. It's along y. The slope coming out of that is essentially the rate of change of that displacement, which is essentially your d by dx of v, which we will call as theta. And then we want to take the second derivative of that, in other words, the first derivative of the slope, and that is essentially your rate of slope change, and that we will denote by kappa of x, and that's essentially the second derivative of v with respect to x, right? And all of these are scalar quantities, the way we are putting it as the measure numbers, and therefore really doesn't matter in with respect to which frame of reference you take it, but once you put the same equations in a vector form, the frame with respect to which you take the derivatives will also become important. Okay. The last thing in this slide that we want to look at is just the curvature we have just introduced, kappa. We want to see the reciprocal of that curvature. What is that? And that's called as the radius of curvature. Again, a topic that you would be familiar with from basic maths courses even in high school. So essentially, if you have one, you can get to the other, either the curvature and or the radius of curvature, and they are inverse to each other. So if one is increasing, the other is decreasing, and so on and so forth. Right? So now let's take that simple example and just say a small length of the beam dx along the overall length L. So you take that length and it's essentially curving like that. And within that small length dx, you can see that the radius of curvature is a constant. Okay, so it can vary from x equal to 0 to L, if you saw that example of the beam over here, the curvature, you see it's kind of flat over here. In other words, the slope is not changing across the center. So essentially the curvature is 0. Okay, so you could have different curvatures at different locations, but here we are taking one small length element dx, because x varies from 0 to L, which is the semi-span, let's say b by 2 in the usual notation. So that's aerodynamic notation. So here we are taking one chunk of the length, which is of length dx, and we are expanding that out and showing in this picture. This is its original configuration when there was no load acting on it, and once there is a load which is pulling it up, it is essentially going to get curved like this, and within that dx, the radius of curvature is going to be a constant, right? And we will call that radius of curvature as rho, and that dx, let's say it subtends at the center of that curvature an angle phi. Okay, now from very basic math, you know that the length dx over here, whatever length you are having, is going to be rho times phi, right? Now it's very clear that the cross section points are not going to behave all the same in bending. So when it's bending, you can see that the top fibers are getting compressed and the bottom ones are getting extended. So whatever length was there earlier, it has become shorter than that for these, and here it has become longer than before. Okay, so somewhere in between, it's quite obvious that because it's a continuous function, there is going to be a location where the length is not going to change at all. Here it is decreasing, that from dx whatever it was, it has become shorter. From whatever dx it was, so this is dx. So this is essentially the undeformed length of that small element. Now it has become larger than that. Here it has become smaller than that. So somewhere in between there should be a location where it remains the same length. Okay, so that's where we are getting into, and we introduce a concept of what is known as the neutral axis. Okay, so that red dotted line, dashed line that you see over there, that is essentially the locus of all the points which are having a zero longitudinal strain. In other words, if there was a longitudinal strain, it would have changed its length. So here the points on this have a negative longitudinal strain. Therefore, the length has decreased. These points on this have a positive longitudinal strain, therefore there is an extension larger length than before. But there are points somewhere in between which have zero longitudinal strain in spite of this bending, and that's the locus of all of that is what we call as the neutral axis. Okay, so now by definition, the neutral axis length is unchanged. So it was rho phi, rho times phi to start with, and remains rho times phi at the end of it as well for that particular red curve that you see over there. Whereas if you take any other location, some positive y, you're going to have compression, which is a negative strain. Okay, and if you go to a negative y, because remember that we had taken x along the length and y which is from the centroid, which is upwards, right? So that's the direction in which we had introduced our coordinate system x, y, and z of course coming out of the plane of the screen. So when you're having something like that, you can very easily see that for positive y, there is going to be a negative strain, in other words compressive strain, and for a negative y, there is going to be a positive strain. So there has to be a negative sign in that particular relationship, which we will see shortly. And how is strain defined? Just like the example that you showed in the homework presentation as well, of the homeworks, you see that it's essentially the change in length divided by the original length. Okay, now for original length, we can take the length of the neutral axis itself, because that length remains unchanged. That is essentially your rho phi, right? So which is the undeformed beam length. Okay, so now your undeformed beam length is rho phi. Okay, that's your initial length, which is the length of the neutral axis as well, which remains the length of the neutral axis at all times. So therefore that is to be subtracted. Okay, what is the new length that you have? That is the new radius of curvature of any arbitrary point you take at some location y. Now that, how far is it from the center, is the neutral axis points are a distance rho from the center, but the point over here is rho minus y, because you have to go back towards the center in a y, essentially in the distance of y, and so essentially you're looking at rho minus y is essentially that particular radius of curvature over there. So rho minus y times the same angle, whether it's a point on the neutral axis, above the neutral axis, or below the neutral axis, the angle subtended there is the same. It's only how far is it from the center that it matters, and if it is as far as rho, then no strain. If anything more than rho, it's a extensional strain. Anything less than rho, it's a contractive strain, right? So this is the new length after deformation. This is its original length, which is the same as the length of the neutral axis, and divided by the original length. That's going to give you your longitudinal strain, change in length divided by original length. And that, if you simplify, you see that rho phi will get cancelled, and what remains in the numerator is minus y phi. Phi can get cancelled and just becomes minus y by rho. And this minus sign, we already explained that for positive y, negative strain is there, that is, it is compressive, and vice versa for the bottom points. Now, we also introduced this concept of the curvature being 1 by the radius of curvature. So there is a 1 by rho over here, which I can replace by kappa, so it just becomes minus kappa y, right? So that minus kappa y, and kappa, there is a complicated equation for that d squared y by dx squared, which is the deformation v of x, so d squared v by dx squared divided by 1 plus dv by dx the whole squared power 3 by 2. So in other words, there is a denominator term for this, which is so your kappa is equal to not just the d squared v by dx squared that is shown over here. Of course, when there is a w and a u as well, this will become partial derivatives, or dou squared v by dou x squared, etc. So there is a denominator term 1 plus dv by dx whole squared per 3 by 2. Okay. So now we are essentially interested in geometrically linear theory, where v is a very small quantity compared to the length, etc. X is of the order of the length, v is very small. So dv by dx is usually very small. The slopes are very, very small. So which essentially means that this dv by dx is small compared to 1. Now you are also squaring it. It becomes even smaller compared to 1. So the denominator is as good as 1. So essentially we are saying that compared to 1, this is approximately equal to 0. And therefore, we are saying that this is an exact equation. So now you get an approximate equation, which is that this is dou squared v by dou x squared in general, but in this 2D, this is for 3D, and for the 2D case, we are just saying it's the ordinary derivatives d squared v by dx squared, because it depends only on x, not on y and z, right? So that's what we have put over here. So this should not be exactly equal, but approximately equal. So that's what we have. And the negative sign, of course, is a fallout from, again, the fact that at positive y there is a compression, which is what is already indicated by the mathematics as well. Okay. So this is an important relationship that we have got to, because we said that v is kind of a measure of the deformation, but also the curvature is an even more direct measurement of a bending deformation, because your axial strain resulting from bending is going to be directly proportional to your d squared v by dx squared. And of course, how far it is from the neutral axis is what determines the actual value of the strain and its sign as well. Depending on the sign of y, it's the opposite sign for epsilon xx. Okay, so now that we have the strain, we can now invoke Hooke's law to get to the stress, the corresponding stress sigma xx, which is straightforward for an isotropic metallic material, for example. We just have to multiply this by E, and then I will get the stress. So in the next slide at the beginning, I will show that I will take this factor, multiply it by E, and I will get the stress sigma xx. Okay, so the purpose of this slide is to get to an expression for the bending moment, which is EI times the curvature kappa. But in order to get to that spot, we need to start from where we left off in the previous slide, which is that we had an expression for the strain. So now we have an expression for the stress as well, which is just for the isotropic material that we are interested in, just the Young's modulus times that strain. Okay, so this is the expression for sigma xx, quite clear from the previous slide. Now we can get to the bending moment, because this stress is what is kind of the as a resultant over the entire cross section, because stress is at each point of the cross section. Now when you are integrating the contribution of the stress to a moment about the neutral axis, each of that is going to contribute. So in other words, I take an element, infinitesimal area element dA in the cross section, and that cross section a stress sigma xx is acting. So the force because of that is sigma xx times that dA. Now the moment due to that is how far is it from the neutral axis, which is distance y, because that is the way we have defined our coordinate axis system, that it's the origin is at the centroid, and display and the coordinate above is essentially your y in the direction in which the load is applied, the load in direction in which the deflections are happening as well, and that distance will give you the moment arm for that force. So there is a location with an area dA around an infinitesimal, it's around an infinitesimal area. So sigma xx times dA is the force, multiplied by y is the moment arm. When we get to that, we get this expression over here. So sigma xx times dA is the force, and that multiplied by the moment arm y gives you the moment because of that infinitesimal element. But now we have to do that for the entire cross section, which means we integrate, it's a double integral actually, over the area of the cross section. And when we do that, after substituting for sigma xx from here, of course, we get this particular expression, right? So now when we have that, you see that there are certain things which are not dependent on the cross section, cross-sectional coordinates, and that can essentially be taken out of this. One is of course the material. It's the same material at all points in the cross section because we're considering a homogeneous beam, so that E comes out. Then it's a curvature, which is a function of the entire beam, because V is a function only of x, and therefore your second derivative of V is also a function only of x, whereas the integrations are going to happen with respect to y and z, which are the cross-sectional coordinates. So that can also come out of the integral. So when that happens, what is left is just an integral of y squared dA, which is nothing but your second moment of inertia about the z-axis, right? So which is what we will call as I, but truly speaking, it should be written as I subscript zz, because essentially it's a second moment, therefore z is repeating twice, and it is also about the z-axis, and therefore the use of the subscript z over there. So once we have that, and we also recognize that this is nothing but your curvature, and which is what we are calling as kappa, you see that that is over there. Okay. So as I said, this is the definition for your second moment of area, not to be even though the symbol used is I, which is kind of misleading. Unfortunately, a lot of textbooks have used this same symbol which they use for the moment of inertia, which is a very important variable, as you might remember from your dynamics course, in order to understand rotational motion. So this is not that. Okay, that has the unit of kilogram meter squared in SI, whereas this has the unit of meter power 4, because there's a meter squared coming from y, and there's a, from the area another meter squared, and total you have is meter power 4. Okay, so this is an important thing. Now, as I said, because we are looking at just the 2D deformation, we have dropped all these subscripts because we understand what each one of them means. But very soon we will be extending this in today's afternoon class possibly to the case of a general three-dimensional deformation of a beam, and when we do that, we will see that it has both an the y and the z direction, in which case we have to be very precise about which I are we talking about, which kappa are we talking about, etc. Okay, which is what I will showcase over here now, that the beam can in general deform in both the cross-sectional directions, y and z. Therefore, here on the other hand, we are only looking at one direction exemplified. We are dropping the subscripts, but let's make sure that we understand what those subscripts are. As I said, there are three quantities which depend only on y, that is essentially your load, your deflection, and now we are looking at three quantities which depend only on the z direction, which is one is the moment, which is about the z direction. The curvature is about the z direction and the moment of inertia is about the z axis. So those are the three things that are related over here, right? And the neutral axis is essentially in the form of a plane. It's a neutral plane because that is essentially defining your z axis, which is coming out of the board in a two-dimensional picture, but here it's shown in a three-dimensional form. Okay. Now, though what we have derived is essentially talking about constant curvature, it's only over a length, infinitesimal length dx. So for the actual beam, it need not be a pure moment problem like this. Any arbitrary loading like you can have in the aircraft, a lift distribution which is elliptical, etc., all of that can also be treated in the same parlance, and all of these equations will still be valid because within that small dx, the curvature is a constant and the derivation that we have done will still be valid. Okay. Now, how to go about finding displacement? We already have three motivations for finding v of x from wide range of problems of application flight vehicle structures. So now we are very close to doing that because we have the strain, we have the stress. All that we have to do is to get to the moment equation, and then from there we will see how the displacement can be found, right? So once again, for that we take a small chunk of material over here of length dx. Now when we are cutting that out and drawing it as a free body diagram, this is essentially how it looks. So this is the whole length of the beam, and I'm just taking a small part of it of length dx, which is the whole length being L, and of course we are introduced the coordinate system x. So I'm taking that dx over here separately. I'm saying that these are, and I want to draw the free body diagram of that. Okay, so the free body diagram, when you draw, you see that each cross section is going to have a shear force and a bending moment. Okay, the shear force is along the positive y direction that we have defined, because this is positive x, this is positive y. So along the positive y is where the positive shear force are there. I already told you. About the z direction you have a moment, about the z direction you have a curvature, about the z you have the second moment of area, right? Now about the y direction, again you have three quantities. One is the transverse load is along the y direction. The deformation that is of interest is also along the y direction, which we call as v of x. And now we'll see that the shear force is also along the y direction. Okay, so that's your shear force. And then there is a bending moment. The bending moment, the positive direction of that is essentially what is going to be along the positive z direction according to your right hand rule, which means it's essentially this. Okay, and here of course there will be something that is reacting to that, which is essentially this. Why this is so is because if you look at the rest of the beam, which is to the left of the infinitesimal moment that we are looking at, that is going to have a similar kind of reaction, and here Newton's third law again applies, equal and opposite reaction, which is why on this you would have something like this, right? Now equal and opposite to that is this, and equal and opposite to this is over here, okay, which is essentially what your curvature is. Now I can take the moment equilibrium of this, I can take the force equilibrium of this, and I can get to certain relationships, okay. Now we saw that it's essentially a lift distribution that you have, an elliptic lift distribution, for example. So there is certain distributed load that is there, which I can call as q of x. Once again the positive, so this is q of x. Now the positive direction is once again along the positive y direction that you have over there. So once you have that, so here you have the shear force, which we will call as v, the bending moment we will call as m, but they will not be the same at both locations because they are at different locations of x. They're going to vary as we move along this small element dx, right? So here it will be v and m, but here it will become v plus dv by dx times dx, and m plus dm by dx times dx, okay? So now I can take the moment about any point, I can take the force equilibrium, and both of those, once I set the limit dx equal to 0, you will see will give me a relationship between q, v and m. The first derivative of m is equal to v, the first derivative of v is equal to q, which is what we will see shortly over here, right? So there are many ways in which we can determine the displacement. The first method that we will talk about is essentially pure integration. Okay, and this integration again could take on two forms. Either you have the form in which you apply the boundary conditions a priori, or you apply the boundary conditions to solve for the integration constant. So in other words, you have either a definite integral or an indefinite integral. So within this you can have two branches, right? So the first step in this is to find the bending moment, that is m, using of course the free body diagram. So and this of course will work only for statically determinate problems. Indeterminate problems, which you already touched upon, you know that we have to first find v of x to be able to actually solve for the entire problem. Okay, so now how do we go about this next? So we have to integrate this particular equation that we already have, that your m by ei is equal to d squared v by dx squared. So if you integrate that twice, very clearly, first time you will get dv by dx, which is the slope. Second time you'll get v of x itself, which is your transverse displacement. Okay. So now we have this is an important equation that we have derived and we have looked at, is essentially your m is equal to ei dou squared v by dou x squared. The partial derivative is introduced so that we can take care of more realistic problems where v is going to depend on other quantities as well other than x. For example, the time in a dynamics problem, or when you're looking at the beam not as a 1D body but as a 2D or a 3D body, either as a plate or as a generic body, then it will become functions of x and z as well, which is why the partial derivative of which the special case that we are looking at here is the ordinary derivative d squared v by dx squared. Okay. So we can just take the curvature to one side and therefore define the curvature in terms of the bending moment, which is m of x divided by ei. So as I said, there are two ways within the integration method. There are other methods other than integration that we'll look at, like solving the differential equation, etc. But right now we are focusing on integration. You can either have definite or indefinite integration. When you're talking of the definite integration, you are applying the boundary conditions a priori, so that once you integrate this one time, this is kappa. When you integrate kappa once with respect to x, you get theta, and therefore if it's a definite integral, you have to apply the limits. So it's theta at some location, arbitrary location x, and starting from one end, let's say, you can say either start from left end or right end. We will see the convenience of doing one or the other when we take up example boundary conditions. But right now, for a generic boundary condition, theta of x minus theta of 0 is going to be an integral of your right hand side over here from between the same integration limits, that is from x equal to 0 to an arbitrary location x, right? So when we integrate that once more, we end up with, because integration of kappa was theta, integration of theta is v. When you integrate that, you get and apply the limits once again, you get the difference between the displacement at some location x to the displacement at this location here. It need not be fixed. It could be any arbitrary boundary condition. If it is fixed, it would be 0, and therefore this difference would directly give you the v at that location. But in general, it is the difference in displacement. Here also it's the difference in slopes between two cross sections. One is an end cross section, the other is the arbitrary cross section at x. Okay, so that's integral of theta of x. That's as far as definite integration is concerned. Very similar is the indefinite integration, where you're just going to add constants of integration at each integration step. Because you're integrating it twice, you will end up with two integration constants. The first time you're integrating this quantity to get to the slope, you will get one equation. So there you can solve, if you know theta at some location x, you can just substitute for that and get to C1. Similarly, if you know the displacement specified at some location as a boundary condition, you can get to your C2 by solving for that. Okay, so that's your displacement equation. Then we will now generalize this to multiple loads. When you have more than one load, here we had only q of x. So when you had only q of x, whatever derivation we did was valid, but we will see that it can be very easily extended to problems where you not only have, let's say, some q naught of x defined, in addition, let's say you have certain concentrated forces, so-called concentrated forces. Let's say, as an example, we are introducing F naught over here, and so-called concentrated moments at different locations, which is your M naught over here. And when you have that, you divide the whole length of the beam L into sections between those concentrated loads. So that whole length L is now broken up into an L1 plus L2 plus L3. L1 is the distance between one end of the beam to the location of the first concentrated force, or any concentrated entity for that matter, force or a moment. So then from that concentrated entity to the next concentrated entity, I call it L2, again, so on and so forth. I've just shown, for example, just 3. It could be any number of finite divisions that you have on the beam along its length. Okay. So what do you do when in this? Now we take advantage of the fact that we are introduce certain assumptions. One is that the material is linear. The second is that the fact that the geometry is linear. In other words, strain displacement relationships we are dealing with are all linear, and therefore the principle of superposition is valid, which is a huge, powerful method. Whenever you have linear problems, you can break it up into smaller problems where you apply only F naught at a time, only M naught at a time. Two separate problems you can easily solve. Then you can solve for a case where only Q naught is applied, and then you can all add them up all. So, or you can treat this part of the beam separately, then you can treat this part of the beam separately, then you treat the third part of the beam separately, and then apply continuity conditions in between them, which is essentially continuity of your displacement and the continuity of your slope, what we call as the C1 continuity. The first derivative has to be continuous. So that's essentially taken care of. When you have this, you can deal with multiple free body diagrams of the L1 section, sorry, not section, but essentially L1 subdomain of the beam, L2 subdomain of the beam, and L3 subdomain of the beam. Each of them you can solve for. So your bending moment will of course be a function of x, but what kind of a function of x it is between these 2 points is very different from an expression that you will have between these 2 points and between these 2 points, because the forces causing that are different, and the bending moment is a function of that, because essentially bending moment is nothing but one of the reactions, the main reaction that is coming from the beam's material points to the loads that you're applying. So the bending moment expressions will be different for the subdomains of this whole length of the beam, namely x from 0 to L. So we'll integrate each subdomain Li. Here we have I varying from 1 to 3, but you can have any number of them, as I said, one by one. So we start with L1, L2, and so on and so forth to the final L that you have, the length Ln of the close to the right end of the beam. Okay. Now if it's a cantilever, we have an advantage, because the kind of boundary conditions that we have over here are essentially conditions which specify the displacement and or rotation, what is known as Dirichlet or Dirichlet boundary conditions, and those will help you give your boundary conditions a priori, and so therefore you can use the definite integral rather than having to go to indefinite integral and having to solve for integration constants later on. You can directly use this approach for a cantilever if you start at the fixed end rather than at the free end. Okay. So when you do that, you know that v equal to 0 over here and theta equal to 0 over here. So you can do the first integration as well as second integration both as definite integrals. So the displacement and slope are known at the fixed end, and therefore straightforward to use the definite integral. So we find the displacement and the slope at the other end of the subdomain, namely at this location. Because I can integrate over this, I know the bending moment expression for this by drawing a free body diagram of that. So I get to this particular location, because I would have already, even before that, first of all, for these external loads, that is Q naught, F naught, and M naught, I would have solved for the reactions over here, because it's a statically determinate problem. I would have already solved for the reactions here. There's a vertical force, there is a moment. I would have solved for them using the force equilibrium, vertical force equilibrium, and the moment about z direction equilibrium. Once I have those, from here I can easily calculate the bending moment as a function of x. I only have to start integrating that. Once I integrate, I get the slopes. Second time I integrate, I get the deflections V, and automatically it's taking care of the boundary condition that V of 0 and theta of 0 are 0. So I just have to keep adding to those zeros, and therefore I arrive at the slope and displacement here. Now that becomes the initial boundary condition for this. Here I knew because it's the fixed support, but here because of the calculations that I have done, I know the initial conditions over here, or in other words the boundary conditions at the left end. So that's going to help me solve similarly for this portion. Then I will know U and theta over, V and theta over here, and from that I can determine V and theta for the rest of the beam as well. Okay, so that's how we end up finding the displacement and slope subdomain by subdomain for the entire beam, for the entire length. Okay, so with this we will conclude. We'll just look at these two lines, break for lunch, and reunite to go for the rest of the review session. Okay, so we use the displacement and slope continuity, as I said, at the interface in order to find the next solutions for the next subdomain, and this we will repeat as many subdomains that are there in this problem, which essentially is determined by how many concentrated loads you have in the problem. Okay, thank you.